Hello everyone, in this video I will demonstrate to you the move instruction in PLCs. But before continuing with the instruction demonstration, first I want to explain to you the data types for the S7 1200 PLCs. The PLC device has many different data types for representing different numerical formats. Here a list of some data types is given below. In the laboratory, you will deal with the bool type, byte, word, and dword type. Okay. There are of course other data types are available, but in the laboratory we will use the first four data type shown in the table. Okay. The first one is bool data type. That's just 1-bit data type, and its range is from 0 to 1. It's a binary signal. Okay. So to call this Boolean data type, or the indexes of the addresses, you know remember from the experiments that we use, for example, for the output Q0.0. Here the dot means you want to access the individual bool. So 0.0 means address value is 0 and the bit index is 0. So by writing Q0.0, you mean that you want to access the 0th bit, the first bit of the address at 0. Okay, and Q means the physical address. Okay, I think we already explained it in a previous experiment. Q is physical output, I for the physical input addresses, and M for the internal memory addresses. Okay, and after this letter you write the address for the memory. For example, address 0, address 1, 2, etc. Okay, and after that, if you put a dot and if you put another number from 0 to 8, you want to access that individual index, and that data type is bool, just 1 bit. Okay, another one is byte, that is 8 bits long, 1 byte. Okay, here also its range is available. It is from 00 to 255. Okay. Here these are the constant entry examples. For example, for the bool you can write true, false, or 0, 1, etc. Okay, if you need to enter some value. Here the byte type is used like that. For example, if you write just Q0, that means you want to access the 0th address, and that address holds a byte. Okay, each address holds 1 byte, so remember that. Okay. For the word data type, this one, its size is 2 bytes or 16 bits. Okay, and here its range is given. Okay, for this one, if you want to use the word data type, you want to write W keyword after the first letter. For example, if you want to use physical output Q, after Q you write W. QW means you want to use word data type. Okay. So QW0 means word at the 0th address. But because each address holds 1 byte, by writing QW0, you control 2 bytes. So that means that you control address 0 and address 1, because each address holds just 1 byte. So if you need another word, for example, for other signals, you have to use QWord2 address this time. Okay, to prevent overlapping. Okay. And similarly, the word is the double of the word. It is 32 bits long. It's basically 4 bytes long. Okay, and to use the double word, you have to write. You have to use the letter D. For example, let's assume that you want to use the internal memory signal. First, you will write M, and after that, you will write D, and after that, you have to write 4. MD4 means you want to access the double word at the address 4. Okay, so this is the data types and the addressing for the S7 PLCs. Okay, S7 1200 PLC. Okay, so in the following parts of the video, I will demonstrate to you the implementation for the experiment. Okay, in the fifth experiment, we will see move instruction. Move instruction is basically used to copy data elements from a previous memory address to a new memory address. and you can use it to convert from one data type to another. The source data is not changed if you are using the move instruction. In the first part, P1 of the preliminary work, we must write a PLC program to set Q00, Q10, and Q11 output after the Q00 is initialized. So we have 3 bits, Q00, Q10, and Q11, and we must set them using I00 input. For this, we have this circuit, okay? So if we activate I00, the move instruction will be activated. So in turn, the output address is QW0. This is this means Q word. This means the physical output word is connected to the as output address of the move instruction. Input value is 259. In binary form, 259 corresponds to 1, 0, 0, 0, 0, 0, and 1, 1. So this means that we will set Q00, Q00, Q10, and Q11 to 1. Okay, so let's see on the ladder diagram. First, we must put our control input I00. Okay, and we must put our move operation. From the right panel, we have here move operation, and move block automatically assigned here. Input is 259 and output is QW0. This means that the physical word Q at the address 0. It is already available on the physical controller board. Okay, the input is connected to 259 and output is connected to QW0 word. Let's load the configuration. And let's enable the monitoring. Alright, you see initially the value for the keyword 0 is 0, but the input value for the move instruction is 259. So now I will activate this input Q00, and you will see that this value will be moved to this address automatically. Let's see. Okay, you see this value is now written onto physical word Q word. Let's see it on the board. You see Q00, Q10, and Q11 is automatically set 1 because this is the binary representation of 259. So by giving that number, we automatically set these 3 bits. In the second part of the preliminary work, we have to implement a ladder circuit where we have to copy the current value of the counter to address using a move instruction. For this, we have first put an up counter here. Its input is I00. Its reset value is also connected to another physical input 01, and its preset value is 3. Its current value, remember that you can get it using the CV output, and we have stored it on the MW10 address. Okay. In the second line, we have implemented a move instruction. Its enable is connected to I02 input, a third input, physical input. Its input is MW10, so this is the current counter value, and its output is connected to MW12. This is the output address. So basically, we will get the counter value from this address, and we will move it to this new address using the move instruction. So let's load it onto the PLC and see the operation. Okay, let's enable monitoring. Alright, now the counter values you see 0. Let's increase it. Now the counter value is 2. Here it is 2, but the next address is still 0. So now I will use the I02 input and I will move this value 2 to this new address. Here you see I have activated it, gave a pass. Now this value 2 is automatically moved to this new address. Now let's increase the counter value 3, 4. Okay. Here you see the input address value become
4, but the output is still 2 because we must activate I02 to move the value like that here. Okay, this is the operation for the second preliminary. In the third part of the experiment, we will use move instruction to determine the preset value of a timer using move instruction. Okay, so here we have this move instruction block. Its input is connected to the integer value 3000, and its output is connected to some address that is memory double 20 address. Okay, this time instead of the word we have used double, which is double the size of the word, and it holds more bigger values. Okay, so moves input is enable input is connected to I00, and here we have a tone timer, and its input is also, let's also put the input for it, I01. We have forgotten to put. Okay, and its preset value here you see is connected to MD20 address. Okay, so now when we activate this input, the move instruction will copy this value from here to this address, and this will set the timer value of this tone timer. Okay, and if the timer is activated, it will activate this output. First, let's load the circuit onto the PLC. Let's load the design. Okay, let's enable the monitoring. Alright, initially you see the value is 0 for this address. So let's enable the move instruction and copy the value. Okay, now we have copied the value here. It is now 3000, but in hexadecimal form. Okay, BB8. Okay, so now let's activate the timer. Now it starts counting. Okay, 3 seconds. So 3000 is copied as the milliseconds. 3000 milliseconds means 3 seconds, and the timer is activated. Let's disable the timer. Okay, and again activate it, and you see again, because this value is still at 3, it is activated after 30 seconds. So using this structure, for example, if the input is some dynamic value, if you can set this value, you can set the timer preset time value of the timer using move instruction. In the last part, we have to implement a ladder circuit where we will get current values of 3 counters at once using move block instruction, and we must store it in an array. Okay, so move block instruction is different than the basic move block, where in the move block instruction data is moved as block. So instead of just one address or just one data, we move the data in block format. Okay, so here we have 3 counters, C2, C3 and C4. Their inputs are connected, count up inputs are connected 0001 and 02, and their resets are also connected. So here the current values of these counters are stored in an array block. So let's see how to create an array block. Here under the program blocks, we double click add new block, and we select data block from here, and we just click OK. Here it is the name of the block, it is data block 2, and click OK, and it is created. Here you can define some variables or some values using the this screen. Here we have to define an array, and I will call it array. Okay, and its data type is here it is bool, given as bool, but we must change it to array type, this one. And using this option, you must define the data type inside the array, and it must be integer for the count values, because the counter values are integers. And the range must be from 0 to 2, because there are 3 counters, so 0, 1 and 2. And click OK. Alright, this is the data block is created. Now let's go back to the main block, and let's connect the current values of the counters we double click and select this area and click this one. Let's first delete this one and see the available blocks. There's a data block 1 and data block 2. We will use data block 2, the newly added block. And inside the data block, here we see the array. We select it. And inside the array, we see the individual elements. For the first counter, we assign iArray 0, the first element. Okay. Similarly, we assign the second element to second counter and the third element to third counter. Okay. And this last line is the move block instruction. These count up inputs 0, 0, 0, 1 and 0, 2 are connected in parallel here to this move block instruction. So either of them will activate this move block instruction. And for the input address, okay, for the input address, we must assign the first address of the array, and it is 0. Okay, count input is the value for how many data will move from one address to another. So here we must move 3 addresses to 3 datas. Because of that, the count value becomes 3. And output address is again the initial address of the array block. Okay. So input is this one and output is this one. So let's load the configuration and see the operation. Must first reinitialize the values. Let's load it. Okay, let's enable monitoring. Okay, this is the first counter, this is second counter, and this is the last counter. Second counter's count value is 1, first counter's count value is 0, and last counter's count value is 0. Let's give pulses to that one and see the operation. Let's change this one to 1. This is already 1, and let's change this one to 2. Let's make this second counter 3. Okay, so now this is 1, 3, and 2. Here, this is the values for, this is the move block instruction. Let's first check the values of the array here. Okay, their start values are 0, 0. You can also monitor this area. Okay, 1, 3, and 2. Okay, this is the current condition. Let's see, because here the move block automatically moves data from one block to another, because we have also connected the count up inputs to the move block. So when you, for example, activate I02 input like that, this also activates the move block, so the data is automatically here loaded onto the array. Okay, like that. So here I am increasing the count values, and you see the move block instruction automatically copies the counter values to that addresses. Okay.